This video will accompany the Chapter 7 notes on sampling distributions. Recall that researchers are often interested in learning about a population. Unfortunately, collecting data from every element in a population can be difficult. Instead, researchers will take a subgroup from the population, known as the sample, to examine. Recall these four important definitions from earlier in the course. In this chapter, we're going to continue to develop a set of tools that will allow us to take the information contained in the sample to say something reasonable about what's occurring in the population. We will accomplish this by studying the behavior of the statistic, then see what the behavior of the statistic suggests about the parameter. Notice that the parameter is the information we really want, but usually only get to observe the statistic. It is vital at this point to emphasize that the vocabulary and notation are essential for this course. Make sure to keep track of the definitions and the ideas. In previous chapters, you already saw the notations for different types of statistics and parameters without realizing it. So notice here in this table, we have all of our notations summarized. What each of these notations are in words can be found at the bottom of page 1, and this table is at the top of page 2. Recall that values calculated from sample data are statistics, and values calculated from population data are parameters. Here again is all of that information summarized. Looking across the rows, we notice that each statistic has a corresponding parameter and vice versa. For example, looking at proportions, we can see that p hat and p are a pair. From this point forward, we can think of each statistic as being paired with a corresponding parameter. We're going to learn how to use the value of a statistic to say something reasonable about the corresponding parameter. Most of the time, we cannot collect population data, and since parameters are calculated from population data, we cannot calculate parameters directly. In cases where the population data cannot be collected, we can only learn about parameters via the statistic, which we can calculate. Recall from Chapter 1, we defined statistical inference as the process of using the information contained in a sample to draw conclusions about what is happening in the population. Now we can be even more specific. We can think of statistical inference as the process of drawing conclusions about the unknown parameter based on the calculated statistic. When we say unknown, we mean that the value of the parameter is unknown. Carefully read each of the scenarios and identify the parameter in the statistic. For each scenario, give the notation and value if the value is known. Notice that the first is solved for you. We'll look at this one together, and then you can pause the video and try B and C on your own. The Kentucky Derby started in the year 1875. Data from all the winners of the Kentucky Derby can be found at the website located in your notes. The average winning time for all winners is 129.28 seconds. A random sample of 20 winners was selected, and the average was found to be 131.45 seconds. First of all, notice that the population is all the winners of the Kentucky Derby. Therefore, the parameter is the average running time of all the winners. The appropriate notation and value here are mu is equal to 129.28 seconds. The sample is the selected 20 winners. The statistic here is the 131.45, the average running time of the 20 selected winners. The appropriate notation and value are x bar is equal to 131.45. Pause the video here and try part B and C on your own. For part B, we have listed here that the population is the games played by all NBA teams in the 2018 playoffs. Therefore, the parameter is the average of points for all games. The appropriate notation is mu, and the value is unknown. The sample is the games played up to 4/28/18. Therefore, the statistic is the average point per games up to that date. The appropriate notation and value are x bar is equal to 94.25. For C, the population is all peanut M&Ms. Therefore, the parameter is the proportion of all peanut M&Ms that are orange. The appropriate notation and value are p equal to 0.13. The sample is the 200 peanut M&Ms. Therefore, the statistic is the proportion of the 200 peanut M&Ms which are orange. The appropriate notation and value are p hat is equal to 26 divided by 200. In section 7.1, we're going to look at how sample proportions vary around the population proportion. If we're going to use the statistic to learn about parameters, we need to understand how statistics behave. Recall in Chapter 4 we discussed random samples. It ends up that if we select the sample randomly, we can say a lot about the behavior of the statistic. We're going to start with an example of a sample mean and then look at a sample proportion. To illustrate how the statistics behave, we will start with an example where we have access to population data. We will be looking at the winning race times for the Kentucky Derby since 1875. First, we will summarize the population data. We start with the dot plot of the population data. So notice here we have a dot plot of every single race time in seconds, winning race time in seconds. And again, this includes every single element of the population. Notice from the population, our population mean is mu is equal to 129.28 seconds, and the standard deviation here is 12.71 seconds. Also, notice that the distribution of the population data is right skewed. Next, we're going to look at a random sample of 30 race times and look at a plot of the sample data. The top plot here is a dot plot of our first sample of 30. For this first sample, the mean winning time is equal to 131.51 seconds with a standard deviation of 14.89. Also, notice that our sample data here is right skewed and that the sample data and the population data on the previous slide look similar. The bottom plot is a second random sample of 30 race times. The mean winning time for the second sample of 30 race times is x bar is equal to 30.38 seconds with a standard deviation of 14.41 seconds. Again, the distribution of the sample data is right skewed. Further, notice that each of the samples dot plots look similar, and they look similar to the population dot plot. We can see that when we take random samples from the population data, we typically end up with sample data that is similar in characteristics to the population data. Our goal is to learn about the behavior of the statistic. For example, the statistic we are interested in here is x bar. Notice that the value of x bar was not the same for each of these two samples. In the first sample, x bar was equal to 131.51, and in the second sample, it was equal to 130.38. Further, neither statistic was exactly equal to the parameter mu. Similar behavior could be seen if we were working with proportions instead of working with means. We have some definitions that we need to know. They are sampling variability and sampling error. Sampling variability is the change in the value of the statistic from sample to sample. Sampling error occurs when the statistic is not equal to the parameter due to looking at the sample instead of the population. Next, we are going to continue the process of taking samples from the population and calculating the statistic from each sample. This needs to be repeated for a large number of samples. We could look at 5,000 samples, for example. So in a picture, what we did was we started out with the population of all Kentucky Derby winners. Then we continually took samples of 30 from that population. So notice each of the darker shapes here looks similar to the big shape, and they represent different random samples taken from the population. From each of these samples, we could calculate x bar. And so notice if we took 5,000 samples, we would have 5,000 x bars. This gives us a long list of statistics. We know that the value of the statistic will vary from sample to sample. The parameter does not change from sample to sample. It is a fixed value of 129.28 seconds. We can visualize the statistics calculated from 5,000 samples by plotting them in a dot plot. So the next plot we're going to look at is a plot of each and every one of these x bars, where each x bar comes from a sample of 30. So here is a dot plot of those means. Notice that the plot of 5,000 statistics is symmetric and bell-shaped. Also notice that the plot is centered at 129.28, the value of the parameter. Plots like this have a special name. They are called sampling distributions. The example above, or here, is a sampling distribution for a sample mean. A sampling distribution is the distribution of sample statistics computed for different random samples of the same size from the same population. A sampling distribution helps us visualize how the sample statistic varies from sample to sample. The above simulated sampling distribution was created as a dot plot. We could have just as easily used a histogram. Alternatively, the sampling distribution of a statistic is the probability distribution that specifies probabilities for possible values the statistic can take. There are certain properties of a sampling distribution that you need to know. First of all, we need to know where its center is. If the samples are randomly selected, the sampling distribution will be centered at the population parameter, and we saw that that was true for the horse racing data. Shape. For each of the statistics on page 2, the sampling distribution will be symmetric and bell-shaped if the sample is large enough. So in summary, we could look at the population distribution, the data distribution, and the sampling distribution. Pause the video here and read about the 3 different types, and then also in your notes is a reference to what these look like visually. Remember, we're trying to understand how the statistic behaves from sample to sample. We can summarize the behavior similarly to how we summarize data in previous modules. The sampling distribution is a plot of statistics and provides a visual summary. Numeric summaries are also useful. We could look at the mean of the statistics and the standard deviation of the statistics. The standard deviation of the statistics is very important because it will help us assess the uncertainty of a statistic in estimating the parameter. In other words, it helps us describe how the statistic changes from sample to sample. The variability of the sample statistic is so important that it gets its own name. The standard error of a statistic is equal to the standard deviation of the statistic. The standard error measures how much the statistic varies from sample to sample. So there are 4 properties we must know about the sampling distribution. We already saw 2 of them. The first is that each of the data points used to create the plot is a statistic, which was calculated from a random sample of the same size taken from the same population. At the center, or mean of the distribution, is the value of the parameter. This is the same as saying that if we calculate the mean of all the statistics, it will equal the parameter. The standard deviation of the distribution is equal to the standard error, and the plot has a symmetric bell shape under certain conditions or certain circumstances, and this usually is whether or not the sample size is large enough. Note, if you take random samples, the sampling distribution will be centered over the actual population parameter. If bias exists, in other words, you do not take random samples, your sampling distribution may give you wrong information about the parameter, and it may not be centered at the value of the parameter. As the sample size increases, the standard deviation of the statistic tends to decrease, and the statistics tend to be closer to the true value of the population parameter. Therefore, we have the 2 following properties. Small sample sizes will produce a sampling distribution with a large standard error, and large sample sizes will produce sampling distribution with small standard error. According to the above, the sampling distribution will be approximately bell-shaped with mean equal to the parameter. There's a fundamental theorem in statistics that informs us that this will always happen under certain conditions. Recall that we will be working with the following statistic parameter sets. The central limit theorem can be applied to describe the behavior of each of these statistics when repeated sampling is performed. We will look at the central limit theorem for some of the statistics above. We're going to start by describing the sampling distribution of the sample proportion. We describe the sampling distribution of the sample proportion by focusing on key features: shape, center, and variability. This brings us to the central limit theorem for a single proportion. When choosing random samples of size n from a population with proportion p, the distribution of the sample proportions has the following characteristics. The mean will be equal to the population proportion p. The standard error, or standard deviation, can be calculated using this formula: p times 1 minus p divided by n and the square root of that quantity. And then finally, if the sample size is sufficiently large, the distribution will be reasonably normal. The larger the sample size, the more the sampling distributions tend to a normal distribution. A normal distribution is a good approximation as long as n times p is greater than or equal to 15 and n times 1 minus p is greater than or equal to 15, which is the same as having an expected count of at least 15 in each category. This box here summarizes the sampling distribution of a sample proportion. Let's now apply these ideas with some examples. According to the 2017 Australian census, P equals 65.6% of students were enrolled in government schools. Assume that we are to take random samples of 50 children and calculate the proportion of children enrolled in government schools. The data comes from the Australian Census Bureau. You can find more information at the link in the notes. So our first question here is, what was the mean and standard deviation of the sampling distribution of the sample proportion of children enrolled in government schools? Interpret these two measures. Well, first, we're going to check our sample sizes to make sure that we can apply the central limit theorem. Notice, checking our sample sizes, we have n times p is equal to 32.8, and n times 1 minus p is equal to 17.2. All expected counts are greater than 15. The requirements for the central limit theorem are satisfied. So now we can calculate the center and the standard deviation. Forgive me, my slides are out of order, so let's do the center first. Let me skip ahead here. All right, so looking at our center, notice the center is going to be equal to p. Well, p is equal to 0.656. This tells us on average, over many samples of 50 children, we would observe a sample proportion of 0.656. Next, we can look at the standard deviation. The standard deviation can be found using this formula. This tells us the expected variability in the sample proportion calculated from many random samples of 50 children is equal to 0.067. And then finally, our question is it reasonable to assume a normal shape for the sampling distribution of the sample proportion of children enrolled in government schools? And the answer here is yes. Remember that we already completed our sample size check, and we saw those requirements are satisfied. So since both these values are larger than 15, it is reasonable to assume that normal shape. Given that P is equal to 65.6% of students were enrolled in government schools, what are the values of the sample proportion we would expect to see or expect to observe from samples of 50 children? Since the sampling distribution is approximately normal, we can apply the empirical rule. Recall that the empirical rule tells us, and this should say 99.7%, of the values fall within 3 standard deviations of the mean. So here, what we're going to do is we're going to apply the empirical rule, and we're going to take the mean plus and minus 3 times the standard deviation. This will give us a range of values for which we can expect the sample proportion to fall in. So this tells us we expect values for the sample proportion to be between 0.455 and 0.857. Next, we could ask, how likely is it that a sample of 50 children will have less than 60% of students enrolled in public school? Well, notice, by the central limit theorem, we already know that the sampling distribution is approximately normal. Since the sampling distribution is approximately normal, we can use the methods that we saw in earlier chapters when working with normal distributions. So this particular normal distribution has a mean of 0.656. We also know that it has a standard deviation of 0.067. Our question here is we would like the area under the curve to the left of 60%, since we're interested in that proportion being less than 60%. So looking at our picture here, here's the normal distribution. Shaded in is the area we're interested in. So previously we saw when we needed to find this area, the first thing we would do is find our z-score. So notice we have the value we're interested in minus the mean divided by the standard deviation giving a z-score of negative 0.84. Then, using your standard normal table, we find this area. You'll find on your table that this area is equal to 0.2005. So this tells us the probability that that sample proportion is less than 60% is equal to 0.2005. So notice this problem is entirely review from our earlier chapters. Take a moment and pause the video and see if you can answer these two questions. For question 1, were you able to find that the mean was equal to 0.79 and the standard deviation equal to 0.0105? Also, were you able to see that it was not reasonable to assume the normal shape since one of our counts was less than 15? Notice here when checking your counts, you do want to check both of them, and if just one of them fails, then it is not reasonable to assume that normal shape. Take a moment and try this example. Were you able to find these values for the population distribution? For the data distribution, were you able to find these two proportions? And then finally, for the mean and the standard deviation, were you able to find these values? In the previous video, we looked at the sampling distribution for the sample proportion. Now we're going to look at it for the sample mean. We describe the sampling distribution of the sample mean by focusing on key features such as shape, center, and variability. Here we have the central limit theorem for a single mean. When choosing random samples of size n from a population with mean mu, the distribution of the sample means has the following characteristics. Center. The mean is equal to the population mean, mu. The standard deviation can be calculated using sigma divided by the square root of n. And if the sample is sufficiently large, the distribution is reasonably normal. The larger the sample size, the more the sampling distribution tends to a normal distribution. A normal distribution is a good approximation as long as our sample size is bigger than or equal to 30. If the population data is normally distributed, the sampling distribution will be normal for smaller sample sizes. This box here summarizes the sampling distribution of the sample mean. Notice here, this summary is for when the population distribution is normally distributed. In cases when the population distribution is not normal, the sampling distribution will usually still have a normal shape, and we'll cover more on this just in a moment. Even when the population distribution is not bell-shaped, the sampling distribution of the sample mean x bar can still have a bell shape. Also, the mean of the sampling distribution of the sample mean is the same as the population mean mu, and standard deviation of the sampling distribution for the sample mean is sigma divided by the square root of n. The bell shape is a consequence of the central limit theorem. Recall the central limit theorem means that no matter what the shape of the population distribution, the sampling distribution of the sample mean approaches an approximately normal distribution. In fact, for most population distributions, the bell shape is approached very quickly as the sample size increases. So for sufficiently large n, we don't have to worry about or even know the shape of the population distribution in order to work with the sampling distribution of the sample mean. In this image, we have a selection of population distributions and corresponding sampling distributions in x bar. So notice here along the top row, these are different potential population distributions. All of them below are sampling distributions. So what we're seeing is as the sample size increases, we see what the sampling distribution looks like for these different population distributions. Notice that the population distributions are very different, but once we reach n is equal to 30, or a sample size of 30, we see that all the sampling distributions are relatively normal. Let's look at an example. Each winter, Peter works numerous shifts as a seasonal waiter at a ski resort in Austria. His salary, including tips, varies from shift to shift depending on the time, or whether the shift falls on a weekday or a weekend. However, experience from past seasons indicates that the salary of the shift will follow a probability or population distribution with mean mu is equal to 150 euros and standard deviation 60 euros. At the end of each winter, Peter randomly selects the pay stubs from 32 shifts he works that season. To check how much he earned on average per shift, he computes the mean salary per shift from the information on these pay stubs. Around which euro value would you expect his mean salary per shift to fluctuate? Well, we would expect it to shift or fluctuate around the population mean, which here is mu is equal to 150. How much variability would you expect in the mean salaries from one season to the next? To find this, we find the standard deviation of the sampling distribution of the sample mean. So notice when working with sample means, our formula for standard deviation is sigma divided by the square root of n. Between what values do you expect 95% of his mean salaries per shift to fall? Well, again, we can apply our empirical rule. And recall that the empirical rule tells us that 95% of the values fall within 2 standard deviations of the mean. So here we have the mean plus or minus 2 standard deviations. What is the probability there is a season when his mean salary per shift falls below 130 euros? Well, notice again, since we know the sampling distribution is normal, we can use the information from previous chapters to find this probability. To do so, we draw a normal curve, which we know is centered at 150. The value we're interested in is 130, and we would like the area under the curve below 130. Computing our z-score, we have 130 minus the mean divided by the standard deviation, giving a z-score of negative 1.89. This tells me the probability that the average salary is less than 130 is equal to 0.0294. Part E is very similar. Pause the video and see if you can work that normal question in a similar way. Were you able to find the probability that the average salary shift per shift falls above 165 euros equal to 0.0793? On the next page of your notes is another set of very similar problems. At the bottom of the page is a solution set for these problems. Pause the video here, work the problems on page 12, and see if you get the same answers. When you return, we'll pick back up on page 13 of the notes. Here we have an illustration of shapes and variabilities. Notice that the population distribution can be more varied, whereas the sampling distribution, the standard deviation of the sampling distribution will be smaller. This shows us there is more variability in the salaries from shift to shift than in the mean salaries from season to season. This example is also discussed in your textbook. The effect of n on the standard deviation of the sampling distribution. Consider the formula sigma divided by the square root of n for the standard deviation of the sample mean. Note that as the sample size increases, the denominator increases and the numerator is fixed. Thus, as the sample size increases, the standard deviation decreases. The implication is that with larger samples, the sample mean tends to fall closer to the population mean, because the standard deviation becomes increasingly smaller. The central limit theorem helps us make inferences. This selection is taken from your textbook. Take a moment and read over this. This concludes the Chapter 7 video.